Hello, welcome to lecture number 49. In lecture 48, we have left one thing pending, which is finding out length of angle bisector. Let us complete that first and then complete the content of lecture number 49. Basically, if we have triangle ABC, and we have bisector, we have seen that the bisector intersects this arc at midpoint L. So this angle is equal to this angle. Let this point be D, this be circumcenter O, and join LC. Okay. In previous lecture we have found out this information about this L point. It is point of concurrency of circumcircle, angle bisector and perpendicular bisector. So now if you observe, AC inscribes angle B at this point and will be inscribing angle B. Therefore we have triangle ABD, similar triangle ANC, right? That is what we have, and therefore this gives us the relation AB upon AL is equal to AD upon AC. And length of angle bisector means we want to find AD or AD square. That is what is our problem today. So AD is basically AB into AC. This implies AB into AC is equal to AD into AL. Now this AL I can write it as AD inside bracket AD plus DI, which gives me AD square plus AD into DI. And therefore I can take AD square to one side. AD square is equal to AB into AC minus AD into DI. AB into AC minus AD into DI. Now AD into DL is also equal to BD into DC, which is AB into AC is equal to BD minus BD into DC. Now in triangle ABC, if this side is small c, if this side is small b, then side BC is getting divided into CS to B. The angle bisector divides opposite side in the ratio of adjacent sides. Therefore D is a point which is dividing segment BC in the ratio CS to B, and therefore distance BD is going to be equal to C upon C plus B times A, and distance CD is equal to B upon C plus B times A. You can find out this by just one argument, that D is a point which internally divides segment BC in the ratio CS to B. You get these answers, which I can replace here. Now AB is going to be equal to small c into small b minus BD is AC upon C plus B into AB upon C plus B. So I can take out C plus B common, BC common, BC inside bracket 1 minus A square upon C plus B square bracket square is the length of angle bisector square. Okay, the only difficulty in this proof is to find out why BD is equal to AC upon C plus B and why CD is equal to AB upon C plus B. You just spend some time on this. It is a section formula. D divides BC in the ratio CS to B. You will get the answer. Total BC is small. Okay, and then this, using similarity, this proof is very simple. This is how we find out angle bisector. So that was the thing which was pending from 48, lecture number 48. Now we move on to the content on lecture number 49. 49 lecture 6. Use of PAPB is equal to PT square. So yet another proof of Pythagoras theorem. We have a circle. Yet another proof of Pythagoras theorem. We have a circle. We have triangle ABC. Now let's see, this line is tangent and we have drawn. So this point is A, point is C, this point is B. So side opposite to capital B, small b. So radius of this circle is small b. This side is equal to A and AB is going to be equal to C. Right? Let us call these 2 points as D and E. So now you see, from B I have a tangent and from B I have a secant. Therefore I can write BC square is equal to BD into BE. Right? So BC square is equal to A square. BD is BA minus small b and BA is C. So BA minus AD into BE is BA plus AE. And AE and AD are same. They are radii. So BA is small c, AD is radius, therefore it is small b, c plus b. We get c square minus, which implies c square is equal to a square plus b square, Pythagoras theorem. Another proof of Pythagoras theorem using PAPB is equal to PT square. Right? Now, after that there is one practice problem, but actually it is a proof of Pythagoras theorem only. We will understand it. What is done is, on a square you draw two right angle triangles and congruent right angle triangles on the two sides. Okay, so this is A, B, C. This is E, D, E, F, and join AD. Let this point be S, let this point be T. Now this is X, this is Y, this is X, this is Y. Both these angles are 90 degrees and this is square. Okay. So in this configuration, now this proof, we will not discuss the geometry part of this proof because it is going to be simple. More important is, this is a craft proof. I mean, if a student actually draws this figure to the scale on a piece of paper or card sheet, and then what we are supposed to do is join AD and cut this figure in two parts. Say ABFD is one quadrilateral and ACED is another quadrilateral. So if we cut it, draw it on card sheet paper to scale, cut it in two parts, and then you can observe that those two parts are actually congruent triangles. You can put this part upside down over here and they will match exactly the same, one on the other. And therefore all these answers, geometric answers, those are asked in these questions, can be easily found out. But moreover, these two diagrams will coincide, and now one way of putting this diagram is this way, and second way of putting it is basically, let me draw one piece the way it is, and the second part also is going to be something like this. Okay, and then if you make some geometry in that, so if I take this part as it is and take this part upside down over here, it can, the figure will look like this. And then if I join a point on the diagonal like this, then this triangle and this triangle, they will be congruent with these two triangles, and you will end up getting two squares, one with side C and another with side B. So basically it is the same piece of paper. If you put it in this fashion, you get two right angle triangles plus bigger square, and in this position you get two small triangles, two small squares on the non-hypotenuse sides of a right angle triangle plus two congruent triangles which are of the same. So area of this total is area of a bigger square, that means square constructed on the hypotenuse, plus area of right angle triangles on the two sides. And here if you see, it is the same area, but it is divided into two right angle triangles, so this and this is same. However, remaining area, that was a total area of the square, is divided into two squares of size which is smaller, and they are of the size non-hypotenuse sides of the right angle triangle. So this is a more visual proof of Pythagoras theorem, but of course there is a geometry involved in it. But I would suggest that students should actually draw this diagram, cut it into two pieces and check whether the area is same, and you get these two kind of figures and Pythagoras theorem is proved. That is what is the content in lecture 49. There is one printing mistake, CP1, major angle ABD. ABD can be any angle, but depending on where you take A, but BAD should have been asked, and it is going to be 45 degrees. So as far as solving problems related to this figure is concerned now, if we just complete the remaining two squares, remaining two right angle triangles outside this, then you will find that it is a square, and when you join this, it is diagonal of the square, and the side of this square, outer square, is going to be small b plus small c. So b plus c sided square, and you have removed two right angles, and therefore you get this configuration. That is what is the story of solving problems. Okay, that is all for lecture number 49. See you in lecture 50. Thank you.